very flat as smooth.
Yeah, there you go. I'd be disappointed if it were any other way.
All right, next question.
All right, welcome everybody. It's my pleasure to introduce today's speaker, Maureen from Yale. Maureen started her career at Rensselaer Polytechnic Institute in upstate New York, where she studied geology and physics. She then went on to receive her PhD from the Massachusetts Institute of Technology in 2006, after which she, fortunately for us, came to Carnegie as a postdoctoral fellow working in geophysics. And after that, she's been an assistant professor at Yale up to the present time. Maureen has received many awards, including a prestigious Sloan Fellowship and most recently an NSF Career Award. And I also note from her CV that not one but two geophysical journals have recognized her for her excellence in reviewing. So next time I guest
Do not send me any more review requests.
Next time I guest at it, I know the target.
Thanks, Diana.
But that aside, it's absolutely lovely to have her back on campus. And today we're going to hear her talk about adventures in anisotropy, probing mantle dynamics with seismic observations.
Thank you very much. Does this audio sounds good? Thank you for that introduction, Diana, and thanks very much for the invitation to come and visit. I always love to come back here, and particularly with this schedule shuffle with the snowstorm last week. I appreciate everyone coming. As Diana said, I'm going to talk today about using observational seismology to get at mantle dynamics problems, and I thought I'd motivate the talk by showing this, very simplified, sort of two-dimensional cartoon view of the relationship between subduction and mantle convection. So this is an open source image. I pulled this off Wikipedia. If you go to Wikipedia and put in mantle convection or something like that, you'll find this image. And I often show this at the beginning of talks because this is kind of our simplified Geology 101 cartoon view, sort of how the mantle works. So we have subduction is a very important driving process for mantle convection. We have slabs that are sinking into the mantle, and these represent the downwelling limbs of the mantle convection system. They also provide the force needed to move the tectonic plates. So we know that sinking slabs play a very important role in mantle circulation and in plate motion. But this cartoon also highlights how little we know about the details of how slabs interact with the mantle. As they go from the surface, perhaps all the way to the CMB. So we know that this, cartoon isn't completely accurate, and it's downright wrong in a couple of its details. But it highlights kind of a host of what I think are very fundamental unsolved problems related to how slabs interact with the mantle around them. So questions like, what controls the path that slabs take through the mantle? We know that slabs don't always sink straight down. Sometimes they flatten out, either in the upper mantle or in the transition zone. How much ambient mantle do slabs entrain with them as they penetrate into the lower mantle? What role do slabs play in controlling the dynamics of the lowermost mantle, if and when they make it to the core-mantle boundary? How is water incorporated into subducting slabs and released into the mantle wedge, or perhaps transported into the deep mantle? And then what role does subduction play in shaping the geologic and tectonic features that we see at the surface? So I'm certainly not going to touch on all of these questions in this talk, but I think a simplified cartoon like this really does nicely highlight a lot of the fundamental unsolved problems that we still have about how slabs interact with and drive mantle dynamics. So what I'm going to try to do today in this talk is talk a bit about seismic anisotropy as a tool for studying mantle dynamics. And then I'm going to talk about two projects that are related to exploiting seismic anisotropy observations in various parts of the Earth's mantle. The first is I'm going to talk about some work looking at seismic anisotropy and mantle flow beneath subducting slabs. And I'm particularly happy to talk about this project in this venue because even though the work I'm going to be talking about today is quite recent. This is a project that really began out of work that I did here at DTM as a postdoc working with Paul Silver. And then towards the end of the talk, I'm going to spend just 10 or 15 minutes talking about some recent work that we've been doing looking at lowermost mantle anisotropy and lowermost mantle dynamics. So just to sort of begin at the beginning, with the definition, what do we mean when we talk about seismic anisotropy? We're just referring to the situation in which the speed at which a seismic wave propagates depends on direction. So this could be a propagation direction, or for a shear wave, it could be a polarization direction. And the picture here is just a photograph of a single crystal of olivine. Olivine is an example of a mineral that has an intrinsic shear wave anisotropy of about 18%. There's about an 18% difference in shear velocity in this direction versus this direction. And it is the dominant constituent of the upper mantle, and we think that olivine plays the crucial role in controlling the anisotropy that we observe in the upper mantle. You can, of course, can imagine if you have, an upper mantle rock that's made of a bunch of individual crystals of olivine. If those crystals are randomly oriented, then on, to a seismic wave that has a very long wavelength of maybe tens of kilometers, that mantle is going to look effectively isotropic. You're going to kind of average out the single crystal anisotropy. What makes anisotropy an interesting tool to study mantle dynamics is the fact that we know that if you take a mantle rock, you take a bunch of olivine crystals and subject it to deformation by shearing it or otherwise deforming it, what happens is that individual crystals of olivine tends to align statistically into preferred directions. And this is known as lattice preferred orientation, or LPO. And this results in seismic anisotropy that is felt by seismic waves. And there's been a lot of work kind of on the mineral physics side of things to work out the relationships between strain or deformation in the mantle and the resulting anisotropy. And this really gives us a tool to go out and measure something about the mantle that reflects deformation. Shear wave splitting is one of the techniques that seismologists have to characterize anisotropy. I think many of you know what shear wave splitting is, in part because a lot of the fundamental work in developing and exploiting this technique was done here at DTM by Paul Silver and others in the 80s and 90s. The idea is that you have a shear wave that is polarized in some direction, like this. It's propagating this way. It's going to hit an anisotropic medium and split into two components that are polarized in different directions. Yes, Em?
I think your mic went off.
Oh, okay. Now you were going to ask me some highly technical question about shear wave splitting. I think you're right. I think my mic went off. The light's still on.
Can everybody still hear her without a
I
mic?
can shout. Okay, I taught a class of 350 people last semester, so I can shout if needed.
I guess if it's
Yeah, you want to try it? Oh, I think the battery's dead. All right, I'm going to shout. Okay. So shear wave splitting. So the idea here is that you have, now your shear wave is split into two, we call quasi-shear waves. So one is traveling faster than the other. And what a seismologist like me will go out and measure is we'll measure the orientation of this fast polarized shear wave. And that tells us something about the geometry of the anisotropy. And then we'll measure the delay time between the fast and slow components. And that tells us something about the strength of anisotropy. So putting this all together, measurements of anisotropy really give us a pretty direct tool for understanding mantle dynamics. And again, the idea is that you have some kind of mantle flow that's going to lead to the lattice preferred orientation of olivine or other anisotropic minerals, or perhaps a shape preferred orientation of things like partial melt, and I'll talk more about that later on in the talk. That's going to give seismic anisotropy on a scale that we can see with seismic waves. And over the past years, particularly on the mineral physics side of things, we sort of developed a set of rules of thumb for interpreting these fast splitting directions. And so a very commonly used rule of thumb is that you go out, you have your seismic station, you measure the splitting of a shear wave that's propagating basically vertically up to your station like this. you measure the orientation of this fast splitting direction. And the rule of thumb is that that is more or less telling you about the direction of horizontal mantle flow beneath the station. Now, I'm presenting a very oversimplified view of this rule of thumb, and people like me spend a lot of our time figuring out, trying to understand the violations of this simple rule. But for a lot of the mantle, this relationship is probably okay, and in particular, for the upper mantle beneath subducting slabs, which is what I'm going to talk about in a minute, we think that this rule of thumb probably holds. All right, so now let's talk a little bit about mantle flow and subduction systems. I'm going to quickly come back to this simplified cartoon. And what I'd like to highlight and talk about is what's going on with mantle flow actually beneath subducting slabs. And this 2D cartoon very nicely shows, encapsulates our classical picture. You have slabs that go into the mantle, they're sinking under their own weight. You have a stiff slab that's sinking into a viscous mantle. And what you get is you get two-dimensional kind of corner flow in the mantle wedge above the slab, and two-dimensional entrained flow beneath the slab, right? You kind of shove a stiff slab into a viscous mantle, it's going to drag stuff down with it. And this is kind of our classical view of what the mantle flow field in a subduction system should look like. And when I came to DTM as a postdoc, one of the projects that I picked up was working with Paul Silver to try to kind of test whether this classical model held up if you look at shear wave splitting observations in subduction zones worldwide. So the question that we set out to answer is to sort of examine shear wave splitting patterns in subduction zones all over the world and ask, do the observations conform to the expectations of this simple 2D model, and if not, what's going on? And so what Paul and I did is kind of go out mostly into the published literature and to try to compile measurements. We did this for the mantle wedge above subducting slabs. What I'm going to focus on in this talk is what's going on beneath slabs. What we did was we went out and said, okay, what observations do we have that can constrain this problem? So, mostly how we did this is we looked at published measurements of SKS splitting. So SKS is a seismic phase that arrives nearly vertically beneath a seismic station, and it samples the entire upper mantle. In fact, it actually samples everything from the core-mantle boundary up to the surface. So it's giving you kind of an integrated picture of anisotropy here. If you want to isolate the sub-slab component, what you have to do is basically apply a correction for what's going on in the wedge. So you can also go out and measure the splitting of shear waves that originate from earthquakes in the subducting slab like this, correct your SKS splitting measurement for the effective wedge anisotropy, and say, aha, what's left over is due to anisotropy beneath the subducting slab. Now, this is tricky, and it's actually, in retrospect, it's even trickier than, we knew it was tricky, and in retrospect, it's even trickier than we thought. And the reason is, the more we think about and work on wedge anisotropy, the more we realize it is hideously complicated, and doing the correction for the effect of the wedge is actually really difficult, which is why now we're using a different type of data that I'm going to touch on in a second. But Paul and I went ahead and did this, and we produced this sort of global compilation of fast splitting directions and delay times, both for the wedge mantle, that's the blue arrows, and I'm not going to talk any further about that, and for the sub-slab mantle, and those are the red arrows. And so what I'd like you to focus on here is looking at the orientation of these red arrows, which shows the fast splitting direction, and compare it to the local orientation of the trench in all of these subduction systems. And the main observation that we made for the sub-slab mantle is that almost everywhere we looked, we found fast splitting directions that were parallel to the trench. Not quite everywhere. There are some notable exceptions. Cascadia up here is one, Mexico here is another, but almost everywhere we looked, we found trench parallel fast splitting directions beneath the subducting slab. If you think back to that simple rule of thumb that I just proposed, in this simple two-dimensional geometry, a slab goes down, it's dragging the mantle with it, and what we would expect from a simple model is to see fast splitting directions that are, parallel to the motion of the downgoing plate. So basically perpendicular to the trench for most subduction geometries. And instead what we find is almost everywhere we look, we see trench parallel splitting. And in order to explain this, Paul and I proposed this sort of simple cartoon view of how mantle flow in a subduction zone might work. And beneath the slab, what we proposed was going on. So you have a slab that's going down. In most subduction systems, the trench is also migrating with respect to the mantle. This is the interpretive dance part of the talk. So if my arms are the slab going down, my shoulders the trench. Usually trenches are also sort of moving around with respect to the mantle. And so the idea is if you have this trench that's migrating, the slab is rolling back, it's basically pushing mantle material out to the side. And you get this kind of three-dimensional flow field around the slab edge. And that gives you, mostly trench parallel flow beneath subducting slabs. So we weren't the first people to sort of propose this. And in fact, back in the 90s, Ray Russo and Paul had published a model similar to this for South America. And what we did was sort of to extend that idea to the global pattern of shear wave splitting and suggest this is the normal state of affairs in subduction systems. There are a couple of ingredients that you need to get this kind of flow field, and I'm going to highlight one of them. This is going to be very important for the work that I'm going to talk about in a second. But basically, we sort of propose that you need some way of decoupling the slab from the mantle beneath it, right? You need a reason. I mean, it's not a silly idea to expect that when you have a slab sinking through a viscous mantle, it's going to drag stuff down with it. That's certainly not an unreasonable expectation. And we said, well, in order to get a mantle flow field beneath your slab that's dominated not by entrained flow, but by this three-dimensional toroidal flow field, you need to have some way of basically mechanically decoupling the slab from the mantle beneath it. And I'm going to come back to that idea in a minute. So we published our model in 2008, and a kind of exciting thing that happened shortly after that is people picked up on our global observations and published a large number of alternative models, alternative hypotheses to explain this preponderance of trench parallel splitting beneath slabs. So there was some work done that proposed that maybe there's a strong contribution from the slab itself if you have aligned hydrated cracks in the shallow part of the slab. A pressure-induced fabric transition in olivine was proposed that maybe at high pressures you flip by 90 degrees that relationship between strain and anisotropy. And then a little more recently, some work done by Alex Song, who's a former DTM postdoc, along with Hitoshi Kawakatsu, suggested that if your geometry of anisotropy in the asthenosphere beneath the slab was different than what we might expect from olivine LPO, and in particular if you have strong radial anisotropy and then you kind of tip that on its side, that might give you trench parallel splitting. And kind of a frustrating thing is that all of these models, if all you're looking at is an SKS, one SKS phase measured at a station on the overriding plate, all of these models make really similar predictions. And so in order to start discriminating among these different models, we need a better type of data set, a better type of observation. And so one of the things that we've been working on in my research group over the past few years is trying to look at shear wave splitting from shear waves that originate from these slab earthquakes, propagate downward into the upper mantle, and that are recorded at far away seismic stations. And the idea is that as long as you correctly account for anisotropy beneath the receiver, on the receiver side, the splitting that you measure is a much more direct measurement of what's going on in the sub-slab mantle. And if you have this type of data, then you can start to put together much more detailed data sets and ask, well, how does the splitting vary as a function of depth? How does it vary along strike? How does it vary with incidence angle and all these kinds of things? And really try to discriminate among all these different models. So we've been applying this technique to several different places. This is work done by Brad Foley, who's a new postdoc at DTM, recent PhD grad from Yale. And Brad did a project with me looking at source side splitting from earthquakes originating in the northern part of the Tonga subduction zone, measured at stations over here in Western North America. And again, the idea is you're measuring, we're sensitive to this anisotropic region directly beneath the slab. A big part of this work is that you have to correctly account for what's going on underneath the receiver. This is not trivial. We spend a lot of time and energy worrying about this, but we think that in the end we're able to correctly account for the receiver side. And a big advantage of this is that we don't have to worry about the wedge, which we know is a huge mess when it comes to anisotropy. So these are some of the results that Brad got beneath Tonga. So what's being shown here, these are maps of fast splitting directions measured at 3 different stations in Western North America, and then this is the entire data set. And you can see that we found evidence for very strong trench parallel splitting. So again, these fast splitting directions that are parallel to the trench, contrary to the expectation of a simple 2D flow model. Pretty large average delay time, so quite strong anisotropy. And an interesting aside from this work is that, somewhat to my surprise, Brad also found evidence for pretty strong anisotropy actually in the transition zone and uppermost lower mantle, which is something that it's not the subject of this talk, something that we're following up on to try to understand if this happens in other subduction zones as well. So since the work that Brad did, we've been applying this to other regions. This is work done by one of my current PhD students, Colton Linner. He published a study last year looking at source side splitting for the Scotia and Caribbean subduction zones, which are 2 regions that have very similar arc and slab morphology, and we thought perhaps very similar mantle flow patterns, and found predominantly, again, trench parallel fast splitting directions throughout most of these systems, with some sort of worrisome exceptions or bothersome exceptions here at the southern end of the Caribbean. And so what Colton did was to try to after we had these studies for Tonga and the Caribbean and Scotia, is that Colton was very eager to kind of extend this to a global compilation, to kind of revisit the work that Paul and I had done with a different type of data. And so recently, Colton has been working on making these measurements for every subduction zone where it's practical to do so. So this is just a map of where stations and earthquakes are for this sort of semi-global compilation of these measurements that Colton has just submitted for publication. And so we can ask the question, do we see trench parallel fast directions everywhere? And somewhat to my surprise, the answer actually is no. So it turns out that trench parallel fast directions, not quite as common as we had initially thought just based on the SKS measurements. So what Colton found is you go to all these different subduction systems and there's a mix. Usually the fast directions are either trench parallel or they're plate motion parallel, not much in between, but it varies and it depends on where you are. So if you go to the Western Pacific subduction zones, this is Izu-Bonin, Marianas, Japan. Through here, they're mostly trench parallel. Here in Ryukyu, we see plate motion parallel fast directions, and here in the Kurile arc as well. The Aleutians, Alaska system are mostly plate motion parallel. Sumatra, we see a pretty profound transition. So here in the eastern part, trench parallel fast directions. Here, they're parallel to the motion of the downrun plate. And then in Middle America, we see mostly plate motion parallel fast directions. So the plot has thickened a little bit, and now we need to have a model that's able to explain kind of this range of behavior. And one thing that Colton noticed right away is that there appears to be a correlation between the splitting behavior we observe for the sub-slab mantle and the age of the downgoing plate. So this is just a schematic of his source side results. So where you see black, that's plate motion parallel fast directions. White are trench parallel. This is just plotted on a map of seafloor age. And we noticed fairly quickly that systems in which you're subducting old lithosphere, older than about 90 million years or so, we tend to have trench parallel splitting beneath the slab. In younger systems, where you're subducting younger lithosphere, we tend to see plate motion parallel fast directions. And so, based on this, Colton has sort of proposed a sort of hybrid age-dependent model, which I'm going to show a cartoon of in just a second. But as I mentioned, a real advantage of this source side technique that you really can't do with SKS splitting measurements is that we're able to do very detailed and quantitative testing of all of these different models for sub-slab anisotropy. What's being shown here, so these are Colton's measurements plotted basically as a function of predictions of all of these different models. So here I'm showing the Aleutians, the Western Pacific subduction zones, Tonga, and then here's kind of a global average. And these are predictions for the Songen-Kawakatsu radial anisotropy model, a simplified 3D return flow model, and then Colton's age-dependent model. Where you see red colors, the model fit is good and the predictions are close to the observations. Where you see blue colors, the fit is lousy. And Colton was really able to show that his hybrid age-dependent model, again, I'm going to talk through what that is in just a second, does a substantially better job at matching the observations than any of the other models that we've considered. Okay, so here's the cartoon view of what we think is going on that might explain this difference with plate age. So we have proposed that beneath young slabs, and again, younger than about 90 million years or so, we have basically the two-dimensional sort of classical flow picture where the slab goes down, it's entraining mantle material with it, and we see fast splitting directions that are basically parallel to the motion of the plate. There is actually likely some three-dimensional flow in these systems, but it's probably pretty deep, and what we're seeing directly beneath the plate is this two-dimensional entrained flow. Beneath old slabs, what we think is going on is that this is basically sort of the long and silver cartoon model, where you have the lithosphere that is going down. There's some mechanism to decouple the slab from the mantle beneath it, so you have, perhaps a thin layer that's acting as this decoupling zone, and you get, if your trench is migrating, which most of them are, then you get this three-dimensional flow field. So it's kind of a twist on the model that Paul and I had proposed a few years ago, but it brings up some interesting questions, because now, of course, you have to explain, why are younger slabs apparently coupled to the mantle beneath them, while older slabs aren't. One thing that I haven't touched on yet, but I want to make sure I say, is that I've shown a bunch of schematic cartoons of this, three-dimensional flow idea, and haven't said much yet about, whether or not this is actually geodynamically plausible. And a very important aspect of all this over the past couple of years has been figuring out, well, can this mechanism actually operate in the Earth, and what are the conditions that might sort of lead to this three-dimensional flow? So what we've been doing is collaborating with some geodynamical modelers. So this is work done in collaboration with Laurent Montesi, who's over here at University of Maryland, and really led by Karen Peskowski, who's a recent PhD grad from Yale, a geodynamicist. And what Karen did was to set up a series of three-dimensional geodynamical flow models that are meant to look like actual subduction systems, and really try to think about, okay, if you have a subducting slab and a migrating trench and some kind of background flow field, is it realistic to get this kind of three-dimensional toroidal flow around slabs? And what are the effects of different parameters, such as the amount of slab-mantle coupling, the dip and vertical extent of the slab, and what this trench migration looks like. And I don't have time to talk through all the details of these models. They're very, very nice. And we've, I think, gotten a lot of insight out of this. But I do just want to show a couple of figures. These are both, I know these figures are a little complicated. These are both oblique views, sort of 3D views of the subduction system. So the slab is here, and it's kind of dipping sort of into the board this way in both of these models. The gray lines are streamlines, so this is showing how the paths that the mantle flow is taking. And one way to sort of make sense of this is to look at the color scheme here. So where you see yellow and white colors, sort of in this sub-slab region, is where we have this trench parallel flow that our model would predict. And you can see in both of these models, we do get this efficient kind of three-dimensional flow around the slab edge with predominantly trench parallel flow beneath subducting slabs. So what Karen's work has shown is that this trench parallel flow, we think it is geodynamically plausible. It's favored by leveling between the slab and the sub-slab mantle. That's perhaps not surprising. It is also favored by steeper slab dips and slabs that penetrate far into the lower mantle. And I want to just quickly say, I've been talking about all of this in terms of mantle flow velocities, which is not very precise. So when we look at anisotropy, we're actually looking at finite strain and deformation and not mantle flow per se. And this is something that we have been looking at using these models. Anisotropy is a function of strain and not velocity, and so we've been computing the distribution of finite strain for these models and showing that indeed the kind of trench parallel flow that we're talking about does result in strongly trench parallel maximum extension. So the bottom line from the geodynamical modeling work is that we think that this is a plausible mechanism. I'm going to wrap up this first part of the talk in just a second and move on to the lower mantle. But before I do, I just want to, hit a couple of points about why this is important. I certainly hope that I convinced you at the beginning of the talk that it's important to understand how slabs interact with the mantle around them. But I also want to touch on a couple of important implications, I think, that this work has, and make it clear why I think it's important that we need to understand what mantle flow does beneath subducting slabs. One reason is that there's a lot of discussion and debate that still goes on about mantle mixing and how well mixed the mantle is, okay? And these are just some figures from a recent geodynamical modeling study by Brandenburg et al. Eric Howry was involved in this study as well. And what they were doing is taking geodynamical models and then trying to understand the amount, how well mixed the mantle and what kind of geochemical heterogeneity you might expect for different types of mantle mixing. And one feature of this model, this is a two-dimensional model, so when slabs go down, they entrain very large amounts of mantle material with them, right? So you have the slab that's penetrating to the mantle, but it's entraining, 10 times its volume in ambient mantle material. And you can imagine that that tends to promote mixing, right? One, I think, important thing to think about is that if that's not the case, if slabs are going down and they're not always entraining large amounts of mantle material, that might have implications for how we understand processes of mantle mixing and how we sort of explain or understand aspects of chemical heterogeneity in the mantle. Another interesting question that I think this work plays into is what is the nature of the oceanic lithosphere-asthenosphere boundary? And this is a great cartoon that I swiped from Nick. I always swipe cartoons from Nick, we all do. Showing some of the processes that have, might be going on at this lithosphere-asthenosphere boundary. And there's a lot of debate right now in the geophysics and geochemistry sort of solid earth communities. What is the LAB? What defines the oceanic lithosphere? Why do we see a sharp, seismic discontinuity in many places at the base of the lithosphere? And this is really, not a problem that's well understood. But if, our ideas are right, and in some cases slabs go down and there's this sort of thin, weak zone directly beneath the oceanic lithosphere that acts to decouple slabs from the mantle beneath it, that definitely plays into our ideas about what the LAB is. And I've been quite coy about what is this mechanism for decoupling, in part because we're still thinking about it. But one of the processes that might be going on is encapsulated in this cartoon, where you have the onset of small-scale convection beneath older lithosphere that might give you a way to sort of decouple the slab that's moving down like this and the mantle beneath it. But I think the larger point is that we really don't understand the oceanic LAB very well, and yet the nature of the LAB is extremely important for the dynamics of what happens beneath the subducting slab. So I think understanding anisotropy beneath slabs is going to play in, I think, to our understanding of what the LAB is. All right, so I'm going to just summarize the first part of my talk on the sub-slab mantle. Our observations show that in subduction zones with older lithosphere, older than about 90 million years, fast directions beneath slabs are dominantly trench parallel. Beneath younger lithosphere, they tend to be parallel to the motion of the subducting plate. We believe that a plausible hypothesis is that you have widespread trench parallel flow beneath old slabs driven by trench migration or slab rollback, and this requires decoupling, and we're sort of working on potential mechanisms, age-dependent mechanisms to do this. For younger slabs, the sub-slab mantle likely remains coupled, and you do get this sort of classical two-dimensional entrained flow. And this is a problem that we're continuing to work on, in particular by continuing this sort of detailed and quantitative testing of different hypotheses, and understanding this physical mechanism for variations in coupling, and exploring the geodynamical implications of what the sub-slab flow field looks like. All right, so I'm going to switch gears a little bit. This is a good time to ask questions. Yes?
Yeah, an astronomer's question. These ages here, these are ages with respect to the distance from the spreading center to
Exactly. It's the amount of time that the lithosphere has spent since. Yeah, and at the actual ages, you know, of course, as they move far away, you know, as the seafloor spreads, as the lithosphere ages, it moves away from the ridge. But it's pretty well known what the seafloor ages themselves are.
So are you thinking of heat as being the discriminant between the younger and the older?
Well, one idea is that you might get this small-scale convection. So the idea is that as lithosphere ages and becomes more dense, it has more negative buoyancy, and there have been a bunch of studies that have looked at the possibility that you actually start to get sort of small-scale convection cells off the base of this oceanic lithosphere. And, you know, sort of by definition, if you have sort of small-scale mantle flow directly beneath the oceanic plate, you're decoupling that plate motion from the mantle beneath it. So that's one age-dependent mechanism. There may be others, you know, other ways to decouple the slab from the mantle beneath it. You know, if you have partial melt there, for example, a very weak layer, it's a little less clear why that would be age dependent. You know, shear heating is one potential mechanism. It's not so clear, you know, so that the asthenosphere beneath the lithosphere heats up via shear heating as it gets older. It's a little unclear whether that can explain the transition at 90 million years. So those are some of the mechanisms, but you know, I have to be honest and say it's not completely obvious what, you know, process or, you know, what changes at an age of 90 million years old that might cause this variation in coupling. So if anyone has ideas, please run it by me.
Just another one following up on what Alan was saying.
Yeah.
Is there any evidence that younger trenches don't migrate as fast as older ones?
Oh, that's a great question. Not really. I mean, the sort of classical idea about slab rollback is that, you know, the older and denser the slab, the more likely it is to sort of, you know, sink rapidly under its old weight and get its own weight and roll back. If you actually look at compilations of trench migration velocities, and these are values that we know fairly well from geodesy. It's actually not really clear that younger trenches tend to be more stationary than older ones.
So
there's not a really clear relationship.
Does that mean that the wedge flow is more efficient in younger trenches, so you don't have to have a flow coming around the sides?
Yeah, that's a great question. It could be. Yeah, I mean, certainly if you're not driving, you know, this three-dimensional sort of toroidal flow, yeah, then it maybe the wedge flow is simpler. You know, another idea, and this is one that I actually favor in part because of all the work that I've done in Cascadia in the Pacific Northwest as part of the High Lava Plains project with folks here. I actually think that in these systems, you know, such as Cascadia, where we think we have this two-dimensional entrained flow directly beneath the slab, I actually think that there is a toroidal flow field, but it's deeper and farther away from the trench, so you might still get this return flow to the wedge, but it's certainly going to have a different geometry and a different set of driving forces. So that would be an interesting thing to look at with wedge anisotropy. Yeah, Larry.
So what you're measuring, what you think you're measuring is the alignment of the crystallographic alignment of olivine that you're then postulating is driven by flow.
Yes.
Does it have to be continuous flow? Could it just be frozen in if you had this toroidal flow once and it's aligned to the crystals and now they're just aligned?
It could be. I mean, if you're not, you know, the anisotropy you see is going to reflect basically the last major deformation episode. So it certainly could be that if you've frozen in an anisotropic structure from past deformation, and then you haven't deformed it further, that's what you'll see. And we think this happens, you know, sort of in the, say, the continental lithosphere, that their anisotropy reflects past deformation. You know, in a region such as, in a setting such as a subduction zone, you know, we expect that there's going to be flow and there's going to be dynamics. But yeah, certainly it's possible. You know, what you're looking at is a sort of time-integrated history, probably over the last couple million years, of what's happened if it's being continuously deformed, and it certainly could reflect a pattern of past deformation as well.
How does your idea of this colloidal flow, how does that scale with the length along the
Yeah,
block of the
great
slab?
question. We haven't really observed any major differences in splitting behavior in, you know, a long strike, you know, short arcs versus long arcs. It's actually something that I sort of expected to see, and we really haven't. So even, you know, a place like Tonga, where, you know, it's long, you know, extensive along strike, we seem to see trench parallel splitting. It's not just at the edges, which in a way is almost surprising.
So I would have thought it's very, very difficult to get a colloidal flow when you've got very long slabs.
Yeah, I would too. Some of the geodynamical models that we've run have shown that even with a long slab, depending on what your background mantle flow is and your trench migration velocity, that you can get
What do you do as far as depth?
flow. Oh, in our models?
Yeah.
We're modeling the upper 600 kilometers of mantle and assuming that there is a barrier to entrained flow at depth. Yeah, and so that's a big assumption. We're currently running some models that have a high viscosity lower mantle in them, and it looks as though the viscosity contrast you need to sort of inhibit this entrained flow, it's about, 70, 80, 100. So on the order of the contrast that we expect between the upper and lower mantle. But that's a little bit of an assumption that's still built into most of the models that we've done. Caroline.
Sorry, you'll never finish your
I
talk.
know, you guys really don't want to hear about the lower mantle.
So, we have more evidence now that we also have anisotropy in the transition zone,
Yes.
and that the path direction is not necessarily the same in the transition zone
Yes.
and above, and so I'm
Yes.
wondering how much of that could possibly be the signal of the transition zone or
Yes.
deeper actually overriding the upper mantle signal. and
Great
cause what
question.
we see.
Yeah, certainly, you guys have looked at this using surface waves. We know from these types of source side measurements, we see splitting. I was sort of astounded when Brad walked into my office and said, I see splitting from, a second of splitting from events at, 660 kilometer depth. And I said, that's not in the upper mantle. So it's a great question. I think what's happening, my sort of own working hypothesis is that deformation in the transition zone and uppermost lower mantle is probably strongest right around slabs, right? So right near where you have this viscous thing impinging on a higher viscosity mantle. I think that for the shallower events in our data set, we're, sampling the transition zone far enough away that, it's not the primary contributor, but that is an assumption. And it's an assumption that we have to look at carefully. Now, with these types of source side measurements, we can look at how the splitting varies with depth. And, so far there's nothing in the observations that have convinced me that we're looking at primarily at transition zone anisotropy, but it's absolutely something that we need to think about. So, yeah, that transition zone, turns out it has all kinds of anisotropy. All right, any more questions on subduction before we switch gears for 10 minutes? Is everybody ready to travel deep into the mantle? Yes, so I'm going to talk in again, I promise this is just the last 10 minutes or so, about some work we've been doing looking at lowermost mantle dynamics. And as with the subduction stuff, I thought I would motivate this with a cartoon. This is a cartoon view of some of the observations and processes that might be relevant to the base of the mantle from Garnero and McNamara. And there's, a bunch of things that are probably going on. We have subducting slabs. Some of them probably impinge on the core-mantle boundary and probably drive mantle flow in various ways. We have likely phase changes. We see ultra-low velocity zones that could be partial melt. And we see these large, low shear velocity provinces, LLSVP. It's a little bit of a mouthful, that have very low shear velocities, but we think that they're not purely thermal anomalies because they appear to be dense, and they don't typically have correspondingly low P-wave velocities. And the work that I am going to talk about now is geared towards getting some observational constraints on mantle flow in the D double prime layer at the base of the mantle. And so the idea is, you know, again, this is kind of the cartoon view. We would love to have some actual observations of what the mantle flow geometries are at the base of the mantle to help, you know, sort of sharpen up our ideas about which of these processes are actually acting. And it's been known actually for quite a while that while, you know, most of the lower mantle is probably more or less isotropic, that we do have at the base of the mantle in the D double prime layer at the, you know, lower 200 or 300 kilometers, that we do have strong anisotropy. And this has been known for a while. I mean, there are observations that go back to the mid-90s of this. But it's been proven to be quite a challenge to interpret it. So we are very definitely not at the point of being able to make measurements of anisotropy in D double prime and say, aha, given what I know about the relationship between, you know, deformation and anisotropy, I can turn that into a mantle flow direction. We are definitely not there yet. There are a couple of reasons this is so. One challenge is that the observations are a little more difficult to make. This is just a summary cartoon from a recent review paper on D double prime anisotropy showing what regions we've sampled looking for anisotropy. And we don't have great coverage looking at D double prime everywhere. And a lot of these studies, you know, basically involve one set of ray paths, right? So you sort of have, you know, a set of events here, a set of receivers here. You're basically measuring shear wave splitting for, you know, kind of one ray path. And then there's an infinite number of anisotropic models that can fit the data. So part of the limitations on this problem are on the data side. Another challenge kind of on the interpretation side is that we still don't know what the mechanism is for D double prime anisotropy. You know, for the upper mantle, we have this framework, and we have, you know, 20 years or longer of experimental studies that have worked out the relationships between strain and anisotropy for upper mantle materials. For D double prime, we don't even know what the mechanism is. So we know that if you have some kind of flow, deformation, or strain at the base of the mantle, we could have this LPO, sort of preferential alignment of individual mineral crystals, or we might have a shape-preferred alignment of elastically distinct properties. So the idea is if you have partial melt and it gets aligned by flow into sheets or tubules or pancakes, that can give you an anisotropy. But we don't know which mechanism is operating. We don't know which minerals are contributing. We don't know the single crystal elastic constants for these minerals at pressures of 125 GPa and, you know, high temperatures very well. And we don't know which slip systems dominate. We don't know the relationships between strain and anisotropy. So I think we've been a little stuck at sort of saying, hey, we have these observations of anisotropy at the base of the mantle, and then turning that into insights about mantle flow has been much harder. So this is a problem that we're trying to tackle, and the approach that we're taking is to try to make some progress on the observational side, and really to put together data sets that give us tighter constraints on the anisotropic geometry than you get with just one set of ray paths. And I'm going to highlight some work that we're sort of is ongoing, looking at anisotropy actually beneath the Afar region of Africa. This is right on the edge of the African LLSVP. These are these big, sort of enigmatic, large low shear velocity provinces in the lower mantle. And we chose to work here in part because it's geodynamically interesting at the edge of one of these LLSVP structures. And also we have reason to think from some of our own work and from work that others have done, that there is strong anisotropy at the edges of these LLSVP structures. So the approach we're taking is to find this one piece of D double prime to try to sample anisotropy from a bunch of different ray paths, and then ask the question, okay, well, which minerals and slip systems and anisotropic scenarios are consistent with the data, and then ask, can we turn that into insights about mantle flow? So the approach we're taking, just to show you a little bit about the data, we're combining two different types of data sets here. One is looking at SKS-SKKS splitting discrepancies. So the idea is these are two different seismic phases that have very similar paths in the upper mantle, different paths in the lower mantle. So the idea is when you go out and measure the splitting of these two phases for the same event station pair, if they disagree, the signal is most likely in the lowermost mantle. And then we're also looking at splitting discrepancies between direct S phases and SCS phases. So this is a phase that bounces off the core-mantle boundary and samples D double prime in a geometry that's almost horizontal. And if you're very clever and can make use of a bunch of different phases, you can account for the anisotropy near the source, the anisotropy near the receiver, and sort of isolate the part that's due to D double prime. These measurements are not easy. I could give a whole nother hour talk on how tricky this is to do, but we think that we do it. And we think that we do it in a way that accurately gets us at D double prime anisotropy. And so this is just a picture of what our data set looks like for this region right next to, so here's the edge of the African LLSVP, this large low shear velocity province. This is directly beneath the Afar region, so there is, we think, a surface expression of perhaps a deep mantle plume here. And this is a look at our data set, so we're looking at stations here in Africa and Europe and events here in the Western Pacific and Eurasia. And we've managed to put together a data set of rays that are sampling this one little piece of D double prime in a bunch of different geometries. And this is just sort of the summary cartoon of what the observations look like. We do see significant splitting that we attribute to the base of the mantle. For SCS phases that are sampling sort of at this azimuth, we see strong splitting with delay times of about 1.7 seconds, fast direction of around 60 degrees. Interestingly, these SCS phases, which are sampling the same spot, just from a different orientation, don't show any splitting at all. So that's telling us something about the geometry of anisotropy. And then we have phases for SKS and SKKS that are sampling, again, at different azimuth and also a different propagation direction, sort of oblique incidence from the horizontal. All right, so let's talk a little bit about what we might see here, okay? And I'm just going to touch quickly on a few of the hypotheses that have been proposed for what these LLSVPs are. They're kind of enigmatic structures. We don't really know what they are, but a few possibilities have been proposed. So one idea actually really invokes the idea of subduction as the main driver for flow at the base of the mantle, and the idea is that these are these thermochemical piles of stuff that might be hot but dense because they're chemically different. And the idea is that you have subducting slabs making it down to the core-mantle boundary, and kind of almost like sweeping up this material into these large piles. And if that were the case, we might expect to see perhaps horizontal flow perpendicular to the edge of these piles, or perhaps a component of sort of vertical flow here at the edge. Another hypothesis is that these LLSVPs are not transient features that are controlled by subduction, but are instead very long-lived features, maybe even primordial features that have been there for a long time and act as sort of anchor structures for mantle flow. And if that's the case, then we might expect to see basically mantle flow deflected by these things. And you might have vertical upwelling at the edge, or you might have horizontal flow sort of parallel to the LLSVP boundary. Another hypothesis, and this is, these are not necessarily all mutually exclusive, is that at the edge of these LLSVPs, that these might actually generate plumes. These might act as generation zones for thermal instabilities that are going all the way up to the surface and are acting as these deep-seated mantle plumes. And so if that were the case, we might expect to see perhaps a cylindrical upwelling or a some kind of other, vertical upwelling in some form. So these are the kinds of mantle flow hypotheses that we can start to think about. All right, so what are the candidate mechanisms? So there are a bunch of different minerals that might contribute. We might have a contribution from perovskite. We might have post-perovskite, which is the high-pressure polymorph for silicate perovskite. We might have ferropericlase. And as I said, we might have a shape-preferred orientation if you have partial melt. And so how do we go about looking at all these possibilities? The approach that we have taken is to sort of take every possible, published set of elastic constants for all these minerals that we could find, and really be, sort of say, we're going to test every possible scenario and every possible orientation of anisotropy that we can think of, and see what fits the data set. So again, we have this set of splitting measurements for a bunch of different directions. We're going to look at all different candidate minerals and orientations and see what fits the data. And this is an example of looking at single crystal elastic constants for post-perovskite from Stackhouse et al. And this is work, I should say, done mostly by Heather Ford, one of my postdocs. And what she's done is sort of looked at all possible orientations of this, single crystal of post-perovskite and picked out which orientations, in terms of inclination and azimuth, are consistent with the data. And I should say that when we started this work, I had no idea how far we were going to get with actually narrowing the possibilities. But it actually turns out that of the, literally like tens of thousands of candidate orientations and elastic constants that Heather has looked at, it's actually a very small number of them that are consistent with the data. And I'm showing you one of the best ones. We actually think that post-perovskite is probably the most likely candidate. So a bit to my surprise and much to my delight, it turns out that we actually are able to use these measurements to dramatically narrow down the possibilities. And specifically, Heather's been able to basically completely rule out any reasonable melt SPO scenario. There's no orientation of aligned melt tubules that are consistent with our splitting observations. We're finding that ferropericlase and perovskite also provide very poor fits to the data. So we, favor the LPO of post-perovskite as the most likely mechanism. And sort of amazingly, we were actually able to settle on only 4 different orientations that fit the data. And that's true sort of no matter whose elastic constants you use. There are a bunch that are out there. Really, there is a very, literally a handful of plausible scenarios that actually fit the observation. So much to my excitement, we actually have been able to dramatically narrow the possibilities. So then, if we have a small handful of orientations that fit the data, then we can say, okay, well, what can we say, if anything, about mantle flow? Here we need to make some assumptions. So we need to make an assumption about what is the most likely slip direction for dislocation creep of post-perovskite. And there's actually a fair bit of consensus in the mineral physics literature, and please correct me if I'm wrong, any of the mineral physics folks in the room, that the 100 axis of post-perovskite is the most likely slip direction. And if that's the case, then we can interpret our candidate orientations of this 100 axis as likely flow directions. And what's kind of interesting is that we were able to basically rule out any horizontal flow direction. There's no inclinations close to 0 here, and instead we found 2 likely orientations that are nearly vertical, and then 2 that are sort of intermediate but have a strong component of vertical flow. And if we then sort of compare these orientations to the set of most likely simplified geodynamical possibilities, I think a really intriguing likely scenario is that we are seeing vertical or nearly vertical flow at the edge of this LLSVP, directly beneath the afar plume. And it's of course a little tempting to sort of try to make the connection to what's happening beneath the surface. Now, can we uniquely constrain that this is what's going on? No. You know, there are other orientations where the flow is not, you know, it's not vertical, it's sort of oblique, that do fit the data. But I think that, you know, we've made a lot of progress in ruling out scenarios for this particular region. And of the simple scenarios that we considered, really the only one that fits the data well is vertical flow. All right, so I'm going to summarize. I think we've figured out a way to put together some fairly novel data sets that sample d double prime anisotropy, and I've been quite excited at how, you know, actually how far we've gotten at ruling in or out different possibilities. We're continuing to work on deep mantle flow beneath the Afar region at the edge of the African LLSVP. We can really rule out some of the scenarios that have been proposed for d double prime anisotropy. Doesn't mean that they're not operating in other parts of the mantle, but in this region, we can rule out melt SPO, we can rule out perovskite or ferropericlase, LPO, and probably horizontal flow as well. And so far, all of the plausible orientations that are consistent with the simplest mantle flow scenarios really suggest vertical flow, upwelling at the base of the mantle, directly beneath the Afar plume, which I think is pretty exciting. I'm going to end there and just leave you again with this, this cartoon, and hopefully leave in your head, I certainly hope I've convinced you that seismic anisotropy is a great tool for looking at mantle dynamics problems, and that there are a lot of, you know, details on this simplified cartoon that we still need to understand. So I'll leave it there, and if anyone has questions about the lower mantle stuff, please hit me.
There was some question about whether post-perovskite even exists.
Yes, there is, and my bias going into this, I actually did some work as a graduate student on LPO of ferropericlase, and between that work and the sort of ongoing debate over whether you actually have post-perovskite in the mantle, you know, particularly right next to an LLSVP where the, you know, it's possibly different from elsewhere in the mantle. My bias actually was that we were not going to settle on post-perovskite, but I have to say that for this data set, it's more consistent with post-perovskite than anything else we've looked at. So my bias was not confirmed. Yeah, Nick.
So given all the corrections we have to do for the crust,
Yeah.
the mantle, the lowermost mantle, how do we do anisotropy of the inner core? There's been a whole
Yeah.
whole number of papers about looking at anisotropy in the inner core. I mean, if you've got all these other things in between you, how do you correct for
Yeah,
that?
that's a great question. I mean, you could ask, of course, the same question about d double prime, and you know, I can sort of say we think we can do it, but there are a lot of assumptions that go into it. You know, for the inner core, most of the constraints come either from normal mode studies, and Caroline actually has done a lot of that, that work, and also looking at just looking at differential travel times of phases that go through the core. But you're right, you have to correct for mantle heterogeneity, you have to correct for the crust, and you know, I don't have a really great answer other than the fact that, you know, we think we can do it, and you know, in particular for d double prime, I mean, there are lines of evidence that, I think strong lines of evidence that you can't explain these observations just with anisotropy in the upper mantle and crust, that there has to be a contribution from the deep mantle, and there's really just no other way. But when it, you know, when it comes to a lot of this, particularly the detailed forward modeling work that I talked about today, a lot, you know, the devil's kind of in the details. I mean, a lot hinges, we're interpreting the details of these data sets, and you have to get the corrections for anisotropy elsewhere along the path right. So I don't have a real satisfactory answer for you, other than that it's a tough nut to crack, and we have to be very careful about it.
Is US array going to really play into that?
I think so. I think having dense array data sets helps. You know, the other thing I think helps is doing, you know, a lot of these measurements now are interpreted just in terms of ray theory, and certainly the modeling scheme that I talked about is ray theoretical. We're not taking into account finite frequency effects. You know, now we have very sophisticated forward modeling, you know, waveform modeling tools that help us, you know, to test some of the assumptions that go in to this sort of ray theoretical approach. So I think, I think that we are going to do a better and better job at testing those assumptions, but it's a big worry. Alan.
Isn't that, just following on from Nick?
Yeah.
Isn't that, aren't those issues compounded, shall I say, by what we were talking about just earlier, that the last layer you go through is...
Yes, absolutely. And that's the sort of the non-ray theoretical part of this, and a lot of the way splitting gets interpreted, and certainly the forward modeling stuff for d double prime that I just showed, we're assuming ray theory. We're assuming, we're not taking into account the suggestion that, say, shear wave splitting measurements are more biased towards the, shallower structure. And again, I think that, we're in a position to make progress on testing those assumptions. We're doing a better and better job of simulating the full wave field in anisotropic media. And we can test to what extent, how much does it matter that your measurements are likely biased towards the surface. So I think we can test these assumptions, but they're important assumptions. They're often unspoken that go into these shear wave splitting observations, for sure. So,
I think Alan Boss
Alan's
has been
got his
for a
hand up,
while.
yeah.
Are there seismic tomography inversions that image the FR plume? You actually show it, and they show the vertical extent as upper mantle only, lower mantle, or
It depends on who you ask, I think. This is true for imaging, for a lot of sort of direct imaging of plumes. These are features that are expected to be, fairly narrow in extent, and it is much harder to image slow velocity anomalies than fast velocity anomalies, because rays tend to, get deflected into fast regions and deflected away from slow regions, just from Snell's law. So there's been a huge amount of debate about whether or not we see, slow velocity anomalies that extend from the surface to the base of the mantle beneath some of these plumes. And it really depends on who you ask. It's not so much a matter of, technically what you're doing in the inversions, it's a matter of interpretation. I mean, there's a school of thought that says these images are so narrow, or these features are so narrow that maybe we shouldn't see them in tomography. There's another school of thought that, says, well, at least in places, if you sort of squint and use the right color bar, you see these vertical anomalies. So the jury's really out. And people have argued about the FR plume in particular, whether or not it's we can see in the tomography. Not a very satisfactory answer, I know.
So actually I just saw a seminar from Andy Blade, and so he did also work about anisotropy along all East African rifts.
Yes.
And his interpretation is that there is from south to north mantle flow.
Yes.
From the African, south of African super plume towards the FR.
Yeah, interesting.
So what do you think about that? And would that change something in your model?
Yeah, good question. I mean, the data set that I presented just now, certainly, we can say something about anisotropy and I think flow for the little postage stamp piece of real estate in d double prime directly beneath the FR. The data set that I talked about doesn't say, really anything about, if that really is upwelling, what happens when it gets to the upper mantle. I think that the upper mantle sort of shear wave splitting measurements that have been made for FR and the surrounding region, I think are pretty convincing in that one potential explanation is that you have this north-south flow sort of towards the FR region. That, may or may not be consistent with the idea, certainly if you want to stretch the interpretation of these measurements and say, well, okay, you have vertical upwelling directly beneath the FR, so it's vertical all the way up. I think that wouldn't be consistent with the sort of model that Andy's proposing, but that would be a, serious interpretive stretch of these observations. And really all I can say is what's going on at the base of the mantle.
And are you going to look at the southern part of the East African rifts? in the near future?
Yeah,
or-
good question. We definitely would like to look at other LLSVP edges.
Because the edge of that zone
yeah,
is actually
yeah.
right in the middle of the two branches.
Yes,
beneath the crater.
yep, it would be great to do that.
It would be great to see if
Yeah, I don't know. The question is always getting data coverage. Any given piece of D double prime, it's hard. You're so limited to where you have seismicity and where you have receivers. It's hard to target regions, but I definitely would love to extend this to other LLSVPs, and I would love to look at slab regions as well. I mean, there are regions where we, think that slab material has impinged on the CMB, and that, that there, slabs should be driving the flow, and I would love to apply this kind of technique to those regions and see what we see. So,
Going back to subduction zones.
yes.
In that global compilation, why are there no observations for South America?
Oh, I'm so glad you asked. I was wondering when somebody was going to call me on that. The ocean's in the way is actually the big, the reason. I'll go. So we make these measurements. They work at epicentral distances of like 40 to 80 degrees or so. Beyond 80, yeah, this is fine. So beyond 80 degrees, you start to sample D double prime, which we know is anisotropic. Closer than 40, your incidence angles aren't really right for shear wave splitting. And the problem, so in this work, we really tried to get ray paths as much as we could that sort of sample, ideally you want ray paths that are taking off, sort of opposite to the dip of the slab, right? And so the South American slab is dipping this way, so you want paths that are taking off here, and the ocean's in the way and there's no stations. And you have to have the right stations to do this in terms of correcting for the receiver. Now, I mean, there are published source side shear wave splitting measurements, and we've actually done, in conjunction with our Peru project, we've actually done some. But you end up mostly using paths that sort of take off this way and go up towards North America. There's a lot more concern about contamination from slab structure. So we didn't include it in this compilation. The ocean's in the way. It's very frustrating.
Any last questions for Maureen? Okay, let's thank her once again.
Thanks very much.